Hello, my students. This is a brief walkthrough talking about Dalton's law of partial pressures and presents a new concentration expression. It's really a concentration ratio, if you will. This is mole fraction, so we will get to that in just a moment. Remember that when gases are together, they each individually behave independently of the other gas. It's as if the other gases aren't even there. The total pressure of the mixture is a result of the addition of the individual partial pressures of your different gases. For example, the total pressure of the atmosphere, or atmospheric pressure, is a result of the pressure of the nitrogen plus the pressure of the oxygen plus the pressure of carbon dioxide, plus the pressure of argon, plus the pressure, and on and on and on, of all the different gases. Because these are parts of the whole, we call them partial pressures. So you may see problems where you're given the different partial pressures, or you may have to find them, and then you'll add them to get total pressure. Or you may be given the total pressure and a partial pressure, and then through subtraction have to find another partial pressure. The pressure is directly proportional to the moles of gas. And we know that based upon the relationship of P equals nRT. The pressure of a gas is directly proportional to the moles within the gas. All right. Well, now this mole fraction. Mole fraction is a ratio of moles, and we're usually talking about the moles of one part compared to the total moles. So the part compared to the whole. So for example, we could get the mole fraction of nitrogen in the air, and it would be the moles of nitrogen compared to the moles of nitrogen added to the moles of oxygen, added to the moles of carbon dioxide, and on and on and on and on. Well, since pressure is directly proportional to moles, we can find mole fraction by saying it's the ratio of moles of one to total, but we can also say that mole fraction is a ratio of pressures, the partial pressure of the gas compared to the total pressure. Or we could collapse and express it in this way. So, looking at these relationships, we can apply, and I have just summarized and typed up for you, but let's go ahead and attack some problems. Mixtures of helium and oxygen can be used in scuba diving tanks to help prevent the bends. For a particular dive, 46 liters of helium at 25 Celsius and 1 atm and 12 liters of O2 at 25 Celsius and 1 atm were pumped into a tank with a volume of 5 liters. Calculate the partial pressure of each gas and the total pressure in the tank. Okay, so in this 5-liter tank, it's asking for the partial pressure that helium shows, the partial pressure that oxygen shows, and then collectively the total pressure. We're taking this gas and placing it in a different volume, and this gas and placing it into a different volume. Well, because I like to rely on the ideal gas law whenever possible, our only true AP chemistry gas law, what I chose to do was to input volume and the original pressure and this temperature to find the moles of oxygen that I had, to do the same but with this different to get the moles of helium. I then could find the new pressure, since I know moles, within this criteria, now that I know moles of helium to get the pressure under with these new criteria. So I'll show you the work that I did for that. So what I did first was found the moles of each given the 1 ATM but the 46 liters for helium, the 1 ATM but the 12 liters for the oxygen. And so this amount of moles of helium and this amount of moles of oxygen. So then what I did was I found then the pressure that each would be showing in the 5 liter. So the 1.9 moles of helium times R times temperature divided by the 5 liter, and so it'll be showing 9.3 ATM, and then plugging in this many moles of oxygen, but in the 5 liter, 2.4 ATM. And then adding those, we would get the total pressure being then 11.7 ATM. However, what we could also do is get the total pressure by taking N total. Yes? N total. So adding our moles and then finding the total pressure this way. And that's just a nice way to reconfirm. And then what you could have done was just found, the moles then, using the moles of oxygen to find the partial pressure of the oxygen, and then subtract to find the partial pressure of the helium. So no matter what, we would have had to find moles somehow, of course, of both, and either adding them to get the total pressure, or finding each individual partial pressure and then adding those to get the total pressure. So you just had to do a couple steps to be able to answer all the questions that you needed. Okay, for this, we are given the partial pressure of oxygen and the total pressure, and it's asking for the mole fraction. Well, pressure is directly related to moles. Mole fraction is either the moles in this case of O2 over N total, or it could be the partial pressure of O2 over the total. As long as the units of pressure are the same, we don't have to do any converting. So all we do is take the 156 torr over the 743 torr. Now notice, mole fraction is just a number. It is a value that could be up to a value of 1. And so we just evaluate the value based upon the actual numerical quantity. And so this gives us some idea of the impact or the fraction, if you will, of oxygen within the mixture. So dividing that, you see here we get 0.210. Just one more example to glance at. The mole fraction of nitrogen in air is 0.7808. Calculate the partial pressure of nitrogen when the atmospheric pressure is 760 torr. So if we have the mole fraction, we're looking for this, and we're told that this is 760. And so just solving for your partial pressure, you will get 593 torr. I've included another tutorial below this that will address some more concerns, if you will, about Dalton's law of partial pressure and mole fraction. But as always, please forward any questions my way.